Europe ridiculed American mills as wasteful, until their forests started collapsing from drought, pests, neglect, and mismanagement, and the irony was inescapable. And that criticism didn't stop at mills. Britain made the same claim about American steam tractors, calling them clumsy, a judgment that would soon face a 60-ton test. What Europe dismissed as wasteful was a machine capable of processing the equivalent of 40 acres of timber a day, a throughput they could never match when their crisis hit. The twist: while Europe burned, the US had quietly perfected a circular timber economy. Laser-guided cuts, 3D scanning, curve saws, and turned bark and sawdust into mulch, heat, and exports. You're about to watch a single log move through a mill that acts more like a Silicon Valley factory than a lumber yard, where nearly 100% of that tree is used, and waste becomes revenue. The question is simple. How did an industry once throwing away 70% end up with almost nothing left in the bin? Why design a road locomotive so massive that detractors called it unwieldy? Because the terrain demanded it, and the workload enforced it. The Case 150 answered a North American problem set: distance, gradient, and freight, where a machine that only shined on metalled roads or showgrounds would simply fail. Across the Atlantic, Britain optimized for different constraints. Heavy, wet soils favored cable plow systems, 2 engines anchored at field edges, hauling plows back and forth with wire rope, while road engines stayed lighter to suit packed lanes and short moves. On quarter sections and open prairies, the calculus flipped. Operators needed mobility, range, and torque on demand, not tethered power. A freighting engine had to haul, stop, refill, and haul again across miles, not yards. The Case 150 read that map and complied. Critics called American tractors clumsy, and by British metrics they were. Lighter traction engines spread less weight, promised less compaction, and excelled in staged demonstrations where a few minutes of high show power masked the limits of small boilers and narrow tanks. But the work rhythm in North America punished short-burst design. Continuous demand exposed undersized heat surfaces, shallow water reserves, and single-speed gearing that left torque stranded on grades. Efficiency means nothing if the load won't move. The Case 150's logic starts at the boiler. Around 180 psi gave the pressure head to keep cylinders fed under sustained pull, while a long firebox stabilized heat input, steady BTUS, not spikes. Water capacity near 650 gallons wasn't vanity. It was uptime. Big coal bunkers meant fewer stops, which preserved thermal equilibrium and saved time where supply points were far apart. Then came the crucial link in the drivetrain: a 2-speed auxiliary transmission that matched torque to terrain. 2-speed mattered because real roads vary minute by minute. Low gear let the engine bite into a climb without over-throttling, keeping adhesion intact and boiler pressure in the band. High gear returned efficiency on flats, lowering piston speed and coal burn while preserving schedule. Showgrounds underplay this reality. A straight, short pull hides the costs of downshifts that don't exist, or water that runs short halfway up a hill. Under the canopy, the design behaved like a system, not a stack of parts. The steam dome skimmed drier steam for consistent admission, reducing water carryover that could rob cylinders of force. Throttle geometry gave the engineer fine control at the moment when slip was most likely. On the takeoff and the first yards of grade, the governor managed speed against sudden load changes, trimming steam to keep the cadence steady. Result: tractive effort that arrived as a firm push rather than a spike that spun the lugs and chewed the roadbed. This systemic approach diverged from Britain's centralized power model. Cable haul plowing concentrated force at field edges and demanded anchors, winch drums, and a choreography of lines that worked best on defined rectangles with known soils. Distributed traction, an engine that carried its power to wherever the work stood, cut those dependencies. On uneven quarter sections, across creek cuts and soft shoulders, mobility beat anchored muscle. Fewer setups, fewer delays, more acres moved, and more freight delivered per hour of steam raised. Here lies the paradox. If the American machine was truly clumsy, Why did its geometry, gearing, and mass align so cleanly with continental logistics? High pressure to feed long cylinders under load. Firebox length for thermal stability. Tanks and bunkers sized to match the geography of scarce water and coal. A transmission that treated hills as part of the route, not as a stunt. The answer was blunt. The Case 150 was not oversized vanity. It was the minimum viable machine for long, heavy pulls where horse teams collapsed and lighter engines stalled. The scale was staggering, but the economics were sober. Fewer trips, fewer stops, fewer failures per mile. The irony was inescapable. The form made sense. But that form demanded nerve to manage heat, water, and throttle at the edge of safe pressure, because the price of this power was discipline, heat, and risk. A cockpit built for hands that could hold a line while the firebox roared. What does it cost to hold 180 pounds per square inch at full pull without crossing the line into catastrophe? The answer was not romance or bravado. It was a checklist, repeated under strain, where every input had a narrow band of safe operation. Heat, water, and motion were linked. Break the sequence and the system punished you. The cockpit functioned as a small economy with two managers. The engineer stood over throttle and reversing lever, reading the load through sound and wheel feel, steering the front axle to keep the path firm and predictable. The fireman worked the fire door and injectors, his timing dictating whether the boiler stayed in its envelope or drifted toward danger. Two roles, one thermal organism. The engine responded to both or to neither. Threats sat close. Let the water fall and the crown sheet, the top plate over the firebox, lost its protective bath, overheated, and failed. Overfire the bed without drawing that heat into work and pressure climbed faster than the system could vent. Snap the throttle and send live steam surging and you risked water carryover and hammer in the cylinders. The irony was inescapable. The power that impressed spectators could, mishandled, become the failure they predicted. Water-level discipline decided everything on a grade. The sight glass and tri-cocks gave the truth, but only if the crew checked them often, cross-referenced, and treated the reading as a moving target while the engine pitched on the hill. Injectors pushed feedwater from the tank into the boiler using steam pressure. Bring them on too early and you chilled the shell, lose pressure, and stall the pull. Too late, and the crown edged into danger. The cadence was practical. Check the glass, feather the injector until the line rose into the safe zone. Close, and reassess as the gradient steepened. The governor translated speed into restraint. Driven by a belt off the crank, the flyweights climbed outward as RPM rose, balls out in the language of the yard, lifting a linkage that trimmed steam admission. It did not add power. It rationed it so parts lived. Under load, as wheel speed dipped and torque demand climbed, the weights settled, the valve admitted more steam, and the engine held a steady cadence. This was not showy. It was mechanical self-control. Firing strategy followed a similar logic. Start with wood to light fast and heat the grate, then move to coal for sustained BTUS once the bed glowed and the boiler came up to working pressure. The fireman shaped draft with damper and stack, opening air to pull hard when the grade bit, closing down to prevent blowing heat up the chimney when demand eased. Overdraft wasted fuel and stripped heat from the plates. Underdraft smothered the bed, sagged pressure, and forced the engineer to reach for throttle he no longer had. Steering and traction lived in the engineer's fingers. Lugged rear wheels needed weight on them and a throttle that came in like a hand on a shoulder, not a shove. Front axle geometry kept the nose pointing where the ground held, avoiding soft spots that turned adhesion into rut chewing. Slip meant heat turned into noise and soil destruction. Gentle throttle, slight corrections, constant feel through the wheel. This was traction control without wires. The system demanded synchronization. Water flowed at the rate the glass required, not the rate the schedule preferred. Fire was managed to the pull, not to the crowd's expectation. Throttle opened to the limit of adhesion, not to the end of the quadrant. Any lapse had a cost. A lifted crown sheet, a pressure spike, a cylinder full of wet steam, a stalled load halfway up a grade that would now have to be backed with care. Operating the 150 then was not brute force. It was a precision routine under pressure. A practice sequence where the crew converted heat into miles with minimal waste and maximal safety. Critics saw bulk and assumed clumsiness. They missed the choreography that turned a large boiler and heavy gearing into steady motion on bad roads with worse loads. Precision established, a bigger test remained. A grade ahead, a freight stack to prove, and an audience waiting for failure that would not arrive on schedule. How do you shut down mockery? You pick a hill, stack 60 tons, and ask a machine to prove a point. Not a fairground, a road with grade, crown, and ruts that pull wheels offline. The Case 150 rolled in with its auxiliary transmission set to low, steel shoes clean, bunker-topped, water at working stock. Eyes on the glass, hand on the quadrant. The test would be plain. Either the load climbed, or the thesis collapsed. Observers lined the ditch and hedgerow as the freight string settled. Chains bit. The sled or wagons, dead weight that punished every loose inch of soil, sat waiting. British engineers had argued that American road locomotives burned coal to heat the countryside, squandering energy through slip and bad gearing, doomed to overheat on a long grade. They favored lighter engines that spared the roadbed, or cable plowing that kept the motive power anchored and efficient. The critique sounded neat. A hill makes it honest. The sequence mattered. Steam raised to working pressure, not a pound more than the safety margin allowed. Water level confirmed above the crown sheet, double-checked as the nose dipped to meet the start of the incline, because a tilt turns inches in the glass into risk at the firebox roof. Low gear engaged. The drawbar stretched to tension, slack taken out deliberately so the first impulse would not snap pins or spin lugs. Then the throttle edged open until the wheels bit without chatter. Physics set the terms. Tractive effort had to exceed rolling resistance plus grade resistance. That's simple, that's severe. Steel cleats pressed into soil, creating shear planes that either held or failed. Mass provided normal force, gearing multiplied torque, and boiler capacity maintained the steam volume needed to keep piston force stable over each stroke. If any one of those fell short, adhesion, ratio, or steam supply, the pull became noise. Under load, the governor's flyweights rose and fell like a metronome with intent. Speed dipped as the gradient climbed. The weights settled inward, the linkage opened admission, and the engine found its cadence. No lunges, no dramatic surges, just regulated delivery. Meanwhile, the injectors clicked on in short bursts, feeding cool water against hot plates at a rate that preserved the waterline above the crown. Too much injector and the pressure sagged. Too little and the roof of the firebox ran hot. The crew held the line. The auxiliary transmission did quiet work. In low, it multiplied torque enough to keep wheel speed modest and piston speed manageable, so every pound of coal purchased forward motion rather than churn. That gearing insulated the boiler from panic firing. Steam generation and steam consumption matched like gears meshing. There was no desperate clawing to rebuild pressure mid-climb. This was the difference between a show pull and a road pull. The cadence stayed steady because the drivetrain allowed it. The load moved. The stack barked in sharp, regular beats that marked each admission and exhaust, a signal that pressure and timing remained in range. The gradient steepened in sections where the lane rose over subsoil. The engineer trimmed throttle by fractions, easing back whenever he felt the rear cleats skate, then adding just enough to rebuild bite. Front wheels traced the firmest line along the crown, avoiding soft shoulders that would steal adhesion and create a yaw that the drawbar would amplify. Behind, weight did what weight does. It tried to fold the effort back downhill. The Case answered with controlled force, not excess. Waterline held, the glass steady in the safe band. Fire bright but not wasteful. Draft set to pull heat through tubes rather than fling it up the stack. Governor kept the rhythm, preventing a rush that could break grip or a lag that would crush momentum. The machine's mass, once mocked as clumsy, now served as assurance. Downforce for the lugs, inertia against stutter. The crest arrived without theater. Chains slackened. Steam eased. The 60-ton string topped the hill under control, with no boilover, no wheeltop polish, no frantic shoveling to mask a failing boiler. The irony was inescapable. The clumsy engine delivered controlled, efficient traction, where lighter designs faltered under continuous real-world demand. With the trial won, the story could have ended in applause. Instead, time intervened. Machines sold, worked, and scrapped, patterns archived in drawings and ledgers. Years later, the silhouette returned, reborn from blueprints and metal, carrying the same lesson up the next grade. What other so-called clumsy machines proved their critics wrong? Tell us below, and subscribe so you won't miss our deep dive on cable plowing versus traction power and the economics that decided who moved the soil, and how. The final irony was simple. The legend had to be rebuilt from blueprints to speak again.